3.6 million pounds. That is the insane combined pulling capacity we're talking about today. Welcome to this explainer. We're jumping straight into the incredible engineering that keeps a massive drill ship, like the GF-12000, safely connected to the seabed in the absolute roughest oceans on Earth. It's a crazy balancing act of brute force and delicate flexibility, so let's dive right in and see exactly how it works.
To break this all down, we'll start with the deepwater dilemma. Look at the anatomy of a tensioner, unpack the high-pressure air spring, map it to a really cool shock absorber analogy, and finally, uncover a hidden silent threat.
All right, Part 1, the deepwater dilemma.
Picture this fascinating contradiction. You've got a massive ship bouncing up and down on the ocean swells, right? But it's securely attached to a 10,000-foot rigid steel pipe that is bolted directly to the stationary seabed. To pull this off without instantly breaking the pipe, the ship's tensioner system needs that immense combined pulling capacity of 3.6 million pounds just to hold the marine riser perfectly suspended in the water column. You literally cannot just bolt that heavy string of steel to the deck. It has to be held dynamically with enormous, continuous strength.
And here's the catch, the ultimate dilemma. If that connection is too rigid when a massive swell hits, the riser is violently overtensioned. That extreme pulling force could quite literally snap the steel. But on the flip side, if it gives way too much and goes slack, the entire 10,000-foot structure just buckles and collapses under its own immense weight. The margin for error here is razor thin.
So how do we solve this? Let's get into Section 2, Anatomy of a Tensioner. The secret to isolating that violent surface motion from the fragile riser below is a ring of 8 dual wireline tensioners stationed right around the ship's moon pool. Each one is capable of extending up to 50 feet. That completely absorbs the ship's heave without transmitting any destructive load spikes down into the pipe. And this entire operation is powered by high-pressure air compressors with accumulator pressure vessels, or APVs, charged to a staggering 207 bar.
Let's do the math on that real quick. That means each individual unit has to seamlessly juggle an average of 450,000 pounds of tension, and it's doing this while dynamically adjusting as the vessel pitches and rolls on the surface. That is a continuous active load that simply never takes a break as long as that riser is deployed.
But raw pulling power alone isn't going to cut it. Since you can't just rigidly pull hard against an unstoppable ocean wave, how do you make these massive machines actually yield and flex? How do you command something holding 500,000 pounds to act like a giant spring?
That brings us to Section 3, the high-pressure air spring.
This is honestly where the engineering gets brilliant. Behind every single tensioner is an APV. It's a critical bank of highly compressed air that acts as a near-ideal, infinitely compressible spring over that massive 50-foot stroke length. Because air can be compressed, it provides a perfectly smooth cushion. A rigid mechanical link would just transfer all that destructive shock straight into the pipe, but the air absorbs it.
It's a continuous, beautiful dance. As the vessel rides a wave up, the piston extends. Inside the APV, the air effortlessly expands and compresses to equalize the pressure, keeping the tension locked safely right in the green zone. And then, as the ship heaves down into a trough, the tensioner piston smoothly retracts. It just flows right with the ocean.
To make this super clear, let's look at Section 4, the shock absorber analogy.
What's wild is how perfectly this extreme deepwater tech maps onto something sitting right in your driveway. Think of the tensioner system exactly like your car's suspension. The goal isn't maximum stiffness, right? It's a controlled, consistent give that smooths out a massive pothole without your wheels ever losing contact with the road. The ocean swell is your pothole, the hydraulic tensioner cylinder is your shock absorber, and that 207 bar of compressed air inside the APV, that is your coil spring, absorbing all the punishment so the chassis, or in this case the riser, stays perfectly steady.
Now, why a 50-foot stroke? That incredible travel margin is specifically engineered for extreme survival drafts and worst-case ocean swells. It grants massive leeway before the system ever risks bottoming out. Under everyday, calm operations, it's only using a fraction of that, but that margin is absolutely crucial for when the ocean gets truly violent. Which leads us to our final part, Section 5, the silent threat.
What's the biggest danger to this incredible setup? Surprisingly, it's not a sudden explosion. When monitoring these complex networks, engineers have to constantly ask themselves, why is a slow, silent drop in air pressure far more dangerous than an immediate system failure with a blaring alarm?
Well, a slow leak gradually depletes the APV's compressible capacity long before it ever hits the low-pressure alarm threshold. It invisibly shrinks the tensioner's safe operating band. If your air spring slowly loses its air, it loses its ability to absorb shock.
all while the system control panels might still technically show a green operational status.
So, how do crews handle this? It requires extreme vigilance. APV pressure absolutely must be logged on strict, fixed schedules. You can never, ever wait passively for low-pressure alarms to go off. Degraded APVs simply cannot absorb the full 50-foot stroke range. If a crew only relies on an automated alarm rather than actively charting those pressure drops, a sudden large heave could quickly push the entire riser into a catastrophic overtension or slack condition, all because that invisible spring just wasn't there when they needed it most.
There's a great quote that perfectly encapsulates this. The greatest threat to this 3.6 million pound system isn't the brute force of the ocean, but the silent, unchecked loss of the invisible air that absorbs it. Our success against the ocean relies not just on building massive iron machines, but on the vigilant maintenance of the invisible air inside them. The iron provides the structure, sure, but the air provides the survival. So, it leaves us with this final, provocative thought. As our deepwater mecha machines grow more and more powerful, can human vigilance consistently outmatch the silent decay we cannot see? In extreme engineering, the biggest dangers are rarely the loudest ones. They're the quiet leaks that slowly rob a machine of its strength. Now that you've got a handle on how these tensioners work, you've completed a crucial link in the chain from the surface all the way to the seabed, which leaves just the massive drawworks left for us to explore next. Thank you so much for joining me for this explainer. I hope it brought a whole new layer of clarity to how we operate in the deepest waters on Earth.